Welcome to the deep dive. Today, we're really getting under the hood of the modern digital world. We're talking about Dell PowerEdge servers, but not just the specs. We want to explore the core ideas, the key tech behind these machines, the things that make everything from e-commerce to big science possible. And we're going to try and cut through the jargon. Our source material for this, it's actually kind of interesting, comes from practice questions for the D-PE-FN-01 certification exam.
Yeah, and what's so useful about that is exam questions, well, they have to boil down really complex stuff to its essence, right? They force you to see the critical points. So it's a great way to understand not just what these bits of tech are, but more importantly, why they matter in the real world, like learning the rules by watching the key plays.
Huh. I like that analogy. Learning by sort of reverse engineering the challenges. Okay, so today we'll be digging into, well, everything from the different physical shapes servers come in to advanced cooling methods, some really vital security bits, and even the different ways data gets stored and managed. The aim here is for you, our listener, to walk away feeling like you've got a much better handle on the backbone of modern IT, the real foundations. Ready to jump in?
Let's do it.
Okay, so first things first, the basics. Because choosing the right type of server is, like, decision number one, right? Just picture it. You need a server for maybe a small doctor's office, pretty quiet, just handling records, sharing files, simple stuff. Now, contrast that with, say, a huge research lab running massive simulations. Weather patterns, maybe. Completely different needs.
Absolutely. And picking the wrong tool for the job can be, well, expensive and inefficient. It really highlights why matching the server form factor to the job is so critical. So for that small office you described, a tower server is often the perfect fit. Our sources point out they're built for places with maybe limited space where noise is a factor.
Right, you don't want a jet engine in the back room.
Exactly. And they often need to be easy to install physically. So quiet, easy setup, great for those basic jobs like file sharing or running a small application. Think of it as a standalone workhorse. Doesn't need a dedicated rack or anything.
Okay, makes sense. The reliable office machine.
But then you flip to the other extreme. You mentioned high-performance computing, HPC. That's a whole different ballgame. For those massive calculations, scientific research, complex modeling, big data analysis, where you need tons of processors working together.
Yeah, serious number crunching.
That's where you look at something like the PowerEdge C-Series. These are high-density servers. They're specifically optimized, really built to cram as many processors as possible into a small space.
So packing maximum power into the rack.
Precisely. Raw parallel processing power is the name of the game. Absolutely essential for those large-scale data centers where every bit of space counts.
So really what this means for you listening is that starting any server project involves a big strategic choice up front. You need to decide, do you need that quiet, easy-to-manage box for a small business? Or do you need that dense processing powerhouse designed for complex, parallel jobs where space and power efficiency are paramount?
It's all about matching the tech to the need. And the budget, of course.
Always the budget.
Okay, so we've picked our server type, we've got the right physical box, but now how do we actually manage these things, especially if they're sitting in a data center miles away or you've got hundreds of them? Imagine like a critical alert goes off at 3 a.m., server's down, maybe hundreds of miles away, and the OS isn't responding at all. What do? That brings us to remote management.
Yeah, and this is where IDRA, the Integrated Dell Remote Access Controller, is just indispensable. Its main job is what we call out-of-band management.
Out of band. Okay, unpack that a bit.
Right. Think of it like having a separate, tiny computer built into the server with its own network connection. It runs independently of the main operating system. So even if the server's main OS crashes, or, get this, even if the server is completely powered off.
Seriously, even powered off. Yep. IDRS is still alive and kicking. It lets you connect remotely, see what's wrong, reboot the machine, maybe even reinstall the entire operating system, all without physically touching it. It's your emergency remote control.
Wow. Okay, that sounds incredibly useful, especially for that 3 a.m. scenario.
Oh, absolutely. Think about it. That server goes dark remotely. Without IDRS, you're probably looking at sending a technician out there. That's time, that's money, that's downtime. With IDRS, you can often diagnose and fix the issue right from your own desk, maybe before anyone else even notices there was a problem. It's a lifesaver for business continuity.
That ability, accessing a server even when it's off or the OS is dead, that really highlights a key concept in server management, doesn't it? This difference between in-band and out-of-band.
It really does. So in-band management is what most people think of first.
Yeah.
You log into the server's actual operating system, Windows, Linux, whatever it's running.
Right, like using remote desktop or SSH.
Exactly. You use the OS to monitor things, install updates, manage apps, but it totally depends on the OS being up and running and the network connection being okay.
Okay, makes sense.
Out-of-band management, like with IDRC, completely bypasses the main OS. It uses that dedicated hardware component, that dedicated network port. It gives you this separate, reliable path to control the hardware directly, even when the main system is completely unresponsive. It's a more resilient way to manage things, especially in emergencies.
Okay, got it. So IDRC is like the ultimate tool for dealing with individual server problems, crises, that sort of thing. But what if you're managing, I don't know, hundreds of PowerEdge servers,
Yeah.
maybe across different sites, and you need to roll out a critical firmware update to all of them? Like now, that sounds like a huge headache.
Oh, it would be, manually. And that's exactly the kind of challenge that Dell Open Managed Enterprise is built for. Our sources highlight it's designed for exactly that comprehensive firmware and driver updates across many servers. But it's actually more than just updates. It's about centralized management for your whole server fleet, really. From one place, you can deploy firmware, drivers, BIOS updates, you can configure hardware settings, monitor the health of everything.
All from a single dashboard.
Pretty much. It saves a massive amount of admin time and effort. Plus, it helps ensure all your servers are consistent, compliant, and up to date. It's about managing at scale, efficiently.
That really paints a picture of how these tools help admins stay on top of things, doesn't it? Moving from just reacting to problems to proactively managing the whole infrastructure, almost like conducting an orchestra instead of just fixing broken instruments.
That's a good way to put it. It enables that kind of proactive, automated governance.
Okay, so we've got our servers picked. We know how to manage them remotely and at scale. Let's shift gears a bit. What about innovation? Pushing performance, keeping things cool under pressure, and locking them down tight against threats.
Right, because the demands just keep increasing. One major area of innovation, especially for those high-performance systems we talked about, is direct liquid cooling, or DLC.
Liquid cooling, like in a high-end gaming PC, but for servers.
Sort of, yeah, but scaled up significantly. The big advantage of DLC is just much, much more efficient heat removal compared to traditional air cooling. As processors and GPUs get more powerful, they generate a ton of heat. And when you pack them densely, air cooling starts to hit its limits. Liquid cooling directly pulls that heat away from the hottest spots.
And what does that enable practically?
Well, it means you can pack those powerful components even closer together. You get higher performance density in a smaller physical footprint.
Ah, so it's not just about cooling, it's about enabling more power and less space.
Exactly. It's kind of fundamental to making things like large AI clusters feasible. As AI and machine learning need more and more dense compute power, traditional air cooling struggles. DLC makes these powerful setups possible, both physically and economically. It lets you push the boundaries.
Fascinating. So we can make them powerful and keep them cool. Now, what about keeping them and the data on them safe? Security is obviously paramount.
Absolutely critical. And a key piece of hardware here is the Trusted Platform Module, or TPM 2.0.
TPM, I've heard of that. What exactly does it do in a server?
So think of TPM 2.0 as a dedicated security chip right there on the motherboard. Its main job is to securely store cryptographic keys. But it's more than just key storage. It helps establish what's called a hardware root of trust. Basically, the server can use the TPM to verify its own startup process cryptographically.
Verifying itself, how does that work?
It ensures that only legitimate, trusted firmware and boot software are loaded when the server starts up. It enables features like Secure Boot. Secure Boot uses the TPM to check digital signatures on the bootloader and operating system kernel, helping to block nasty things like rootkits or other malware that try to hijack the boot process before the OS even loads.
So it's building trust right from the hardware level, from the moment you press the power button.
Precisely. It provides that foundational layer of integrity and security, protecting sensitive data and ensuring the system hasn't been tampered with.
That's some serious protection. Okay, practical question though. Even with all this great tech, things can still go wrong. Sometimes does the server give you, like, simpler clues?
Oh, definitely. You just need to know what to look for. Our sources mention a common scenario. An IT tech is looking at a server rack, maybe troubleshooting, and notices a hard drive bay showing a constant amber LED.
Okay, an amber light. Not usually good news.
Right. On Dell PowerEdge servers, a steady, constant amber light on a drive bay typically means one thing: a drive fault.
Meaning the drive has failed.
Either it's failed completely, or it's predicting an imminent failure. Either way, it needs attention urgently. It needs to be checked and likely replaced to prevent data loss. It's a clear visual warning sign.
Got it. So even a little light can be a critical piece of information. Pay attention to the blinky lights.
Always pay attention to the blinky lights. They're often the first sign something needs looking at.
Right. Let's move into another fundamental area. How data actually gets stored and accessed, and how these machines boot up in the first place. These choices have huge impacts down the line.
Definitely. When you talk about shared storage, two big acronyms always come up: NAS, Network Attached Storage, and SAN, Storage Area Network.
NAS and SAN. I know they're different, but the distinction can be a bit fuzzy sometimes.
It can be. The core difference, according to our sources, really boils down to the level of access. NAS provides file-level access.
Meaning like accessing shared folders over the network, like mapping a network drive.
Exactly. Your computer sees it as a file server. You access files and folders. SN, on the other hand, provides block-level access.
Block level. What does that mean in practice?
It means the server treats the SAN storage almost like it's a local hard drive connected directly to it. It sees raw storage blocks, not files. The server's operating system manages the file system on top of those blocks.
Okay. So NAS is like accessing files remotely, and is like having a remote hard drive appear local to the server.
That's a good way to think about it. And this difference is really important for performance because SANs offer that direct, low-latency block access. They're typically used for things that need high performance, like databases, heavily used virtual machine storage.
Performance-critical stuff.
Right. Whereas NAS is often great for general file sharing, backups, things that are less sensitive to tiny delays. It's a fundamental architectural choice, depending on what the storage needs to do.
That really clarifies the NAS versus SAN decision. Okay, sticking with fundamentals, how the server actually starts up, the boot process, how has that evolved?
That brings us to UEFI, the Unified Extensible Firmware Interface, versus the old-school BIOS. UEFI is basically the modern replacement for the traditional BIOS that computers used for decades.
And why the change? What does UEFI do better?
Several key things. One big one our sources mention is support for boot drives larger than 2 TB. The old BIOS used a system called MBR, Master Boot Record, which had that 2 TB limit. UEFI uses GPT, UAME partition table, which supports vastly larger drives, essential today.
Okay, so bigger drives. What else?
Security is another huge improvement. UEFI enables things like secure boot, which we touched on with the TPM.
Right, checking the signatures during startup.
Exactly. And make sure only trusted code runs during the boot process, which helps block certain types of malware that BIOS couldn't easily prevent. UEFI also generally offers a more flexible pre-boot environment, often with graphical interfaces, network support before the OS loads, and better compatibility with modern hardware. It's just a much more capable and secure foundation.
So moving from BIOS to UEFI wasn't just a minor update. It was a significant step up in capability and security.
Absolutely, a foundational shift.
Well, okay, these choices, NAS versus SAN for storage access, UEFI versus BIOS for booting, they seem small, maybe, but they have massive implications for how well systems perform, how secure they are, and how easily they can scale. Really the bedrock of the whole setup.
So maybe consider, what new possibilities do technologies built on these foundations open up next? And how will these kinds of architectural decisions shape the innovations we haven't even thought of yet?
That's a great question to ponder. Definitely food for thought. Until next time, keep exploring, keep questioning, and we'll catch you on the next deep dive.